Alrighty, so for the first part, or for this problem, we assume that we have some equation, z equals f of xy, that can also be expressed as z equals g of r theta in polar coordinates, using the substitution x equals r cos theta, y equals r sine theta. For the first part, we want to find dr by dx and d theta by dx by assuming that r and theta are functions of x and y. So the first thing that we can do is actually recognize that in our polar form, our polar coordinates, r, we can think about that as being the radius, is going to be the square root of x squared plus y squared. And theta is going to be arctan of y over x. Same thing as tan inverse, tan negative 1, y over x. So we can take the derivative of r with respect to x here pretty directly. We'll have 1/2 of x squared plus y squared, to the power of negative 1/2, we're applying chain rule here, times the partial derivative of x squared plus y squared with respect to x, so that's going to be 2x. And then simplify that. It's going to give us x over the square root of x squared plus y squared. Then going back to what we had above, we recognize that we have r equals the square root of x squared plus y squared, and x is r cos theta. So we get r cos theta over r. So that means that dr by dx is going to be cos theta. Next, doing d theta by dx, the derivative of arctan of y over x with respect to x is going to be negative y over x squared plus y squared. Then we have that y is r sine theta, so we have negative r sine theta on top. On the bottom, x squared plus y squared is the same thing as r squared. We have negative r sine theta over r squared, which is going to give us negative sine theta over r as our d theta by dx. For part B, we're going to do the same thing, but with respect, or for dr by dy and d theta by dy. So for dr by dy, the first step in the process is going to be the exact same, except we're going to end up with y over root x squared plus y squared instead. So we had that y is r sine theta, so you'll get r sine theta divided by r, so we're going to get sine theta as our dr by dy. Next, the partial derivative of arctan of y over x, or tan inverse of y over x with respect to y, is going to be x over x squared plus y squared. Then using our substitutions, x was r cos theta, so we have r cos theta on top, divided by, again, x squared plus y squared is r squared, so we have cos theta over r as our d theta by dy. Next, for part C, we want to find dz by dx and dz by dy. So starting out with dz by dx here, applying what we know about the chain rule for partial derivation, dz by dx, where we're assuming that essentially we're saying that z, so we have d by dx of z of r of xy, theta xy. So z is a function of r and theta, but r and theta are functions of x and y. We're taking the derivative with respect to x. What we'll have is the partial derivative of z with respect to r, multiplied by the partial derivative of r with respect to x plus the partial derivative of z with respect to theta times d theta by dx. So we had from up above that dr by dx is cos theta. So we'll have our first term is going to be cos theta zr, where the subscript of the variable indicates that we're doing a partial derivative, plus, or rather, actually it should be minus, because we had that d theta by dx was negative sine theta over r. So we have minus sine theta over r times z sub theta. That gives us our dz by dx, and we also wanted dz by dy. So dz by dy is going to be I guess I can write it like this. So it's going to be the partial derivative of theta with respect to y multiplied by the partial derivative of z with respect to theta plus r sub y z sub r. So we know from what we did in part B that the partial derivative of theta with respect to y was cos theta over r. So we're going to have cos theta z sub theta over r plus dr by dy was sine theta. So we have plus sine theta z sub r. Now for part D, we are going to have, in part D, we are confirming, and I guess in a sense for all the parts we've been just confirming existing equations, but for part D specifically, we want to confirm that the partial derivative with respect to x squared plus the partial derivative with respect to y squared is equal to the partial derivative of z with respect to r squared plus 1 over r squared times the partial derivative of z with respect to theta squared. So what we can do here, we have that zx squared plus zy squared is going to equal what we're going to do, or the approach that I'm taking. It's going to be essentially plugging in what we found for dz by dx and dz by dy into those squares, expanding them out. So dz by dx squared is going to be, looking back up here, so we're going to have cos squared theta zr squared minus 2 sine theta cos theta over r times zr z theta plus sine squared theta over r squared z theta squared. Then looking at our dz by dy, we'll have, I'm going to keep writing, this is still the same equation as up above. This is going to be cos squared theta z theta squared over r squared plus 2 sine theta cos theta zr z theta over r plus sine squared theta zr squared. Now looking at our terms, first of all, we can see that we have minus 2 sine theta cos theta zr z theta over r. Then we have a plus 2 sine theta cos theta zr z theta over r. So those will add together to 0. Then, if we collect terms we look first, collecting the terms of, or the multiples, the powers, or not powers, excuse me, the terms involving the zr squared, we'd get cos squared, or sorry, we'd get zr squared times cos squared theta from this term. And we'll have plus sine squared theta from this term. And using the Pythagorean identity, we know that cos squared theta plus sine squared theta is always equal to 1. Then we have plus our z squared thetas. We'll have sine squared theta over r squared plus cos squared theta over r squared. So again, we'd apply the Pythagorean identity. We can bring that r squared in the denominator out. So we'll end up getting zr squared plus z theta squared, z theta squared over r squared, confirming the equation that we wanted to confirm. Now, part E here is going to be the most challenging part, the part that's going to take the most time. So, for part E, we want to show that if the second derivative of z with respect to x plus the second derivative of z with respect to y is equal to 0, that then implies that the second derivative of z with respect to r plus 1 over r squared times the second derivative of z with respect to theta plus 1 over r times the derivative of z with respect to r is going to equal 0. So, first of all, we need to try to find the derivative, or the second derivative, of z with respect to x. We want d by dx of our already known zx. Now, zx was z sub r sub x plus z sub theta sub x. In case it's unclear, when I say the sub, that's just describing, okay, we're doing the subscript, and then we're using that subscript notation for the partial derivatives. Now, we need to apply the product rule as well as the chain rule. But first, what I'll do first is apply the product rule, rather. So, we'll have the partial derivative with respect to x of zr multiplied by rx plus the plus z sub r times the partial derivative with respect to x, r sub x. Then we'll have the partial derivative with respect to x of z theta times theta x plus the partial derivative, plus z theta times the partial derivative with respect to x of theta x. Having that, we then need to expand that out further, because we'll need to apply our implicit differentiation to the zr and z theta, as well as, I believe, we'll need to do that for the... No, we don't need to do that for the rx. So, I'll bring the rx out front of this first set of brackets. So we have rx our first will be the partial derivative of zr with respect to r. So that's going to be our second derivative with respect to r times rx plus the partial derivative of zr with respect to theta times the derivative of theta with respect to x. Then we have plus our zr. Now we'd have this was the second derivative of r with respect to x. I'll write that as rxx. We have plus, put the theta x out front. We'll have z theta, or rather dz theta by d theta, then theta sub x plus dz theta by dr times r sub x. And lastly, we'll have added on plus z theta, theta xx. So we can then go and start plugging in what we actually know here. So we already know what the derivative of r with respect to x was. That's cos theta. Then we'd have our second derivative of z with respect to r, which is going to be unknown. We can't really say what that is any further. Then we have times cos theta from that r sub x there. And we have plus zr theta, a mixed partial derivative, times theta x, where theta x was negative sine theta over r. So I'm just going to correct this. So that'll be minus zr theta times sine theta over r plus, I'm going to change around the order of things a little bit. I'll keep these two rxx and theta xx terms. I'll add them on at the end. So then we have our theta x times the next bracket. So that's going to be minus sine theta over r times, we have z theta theta, or z sub theta theta, times our theta sub x. So we're going to need to correct that again. So that's going to be negative sine theta over r, z sub theta theta, plus our rx was cos theta. We have plus cos theta, z theta r. And lastly, we have plus zr. Now we'd have the rxx. So this the rxx is not going to be necessarily immediately trivial. We'll get to that in a second here. The rxx is going to be, need to pause for a second here. So applying our implicit differentiation and it's just the implicit differentiation to that r sub xx term, that is going to turn into, keep in mind, we had that r sub x is cos theta, so we're taking the derivative of that again. So we'll have d cos theta by d theta, and then that's going to be multiplied by d theta by dx. Then our z theta, theta sub xx term is going to be z theta times d by dr, negative sine theta over r, times r sub x, plus d by d theta, negative sine theta over r, times theta sub x, which means that we'll need to rewrite this yet again for adding in the extra terms. But what I'll do instead is I'm just going to copy and paste this. We have cos theta, sine theta, and everything there. Our need to plug back in, we had, first of all, we have d cos theta by d theta is going to give us negative sine theta. We have negative sine theta there. And then d theta by dx was negative sine theta over r. We'll have negative sine theta times negative sine theta. So we'll have a sine squared theta, positive, divided by r in there. Then we'll have the partial derivative of negative sine theta with respect to, or negative sine theta over r with respect to r. That is going to turn into, that's going to be positive sine theta over r squared. It's being multiplied by r sub x, so that's going to be sine theta cos theta over r squared. R squared there. Then we'll have negative sine theta over r, partial derivative with respect to theta, would give us negative cos theta over r. We have plus negative cos theta over r. Then we're multiplying by theta sub x. So that's going to give us another negative sign. So the negatives are going to cancel. And we'd have the, that was a sine, okay, that was cos that we had there. And theta x, okay. So theta x was negative sine theta over r. So we'll have positive cos theta sine theta over r here. Next, one moment here. Oh, excuse me, I just realized, since we were taking the derivative of r there, we have a power of r contributed from the negative sine theta over r, and we also have a power of r being contributed from the theta sub x, so that should be r squared down there. So really, that z theta term we can simplify down a little bit further. That's going to be 2 z theta over r squared times sine theta cos theta. Unfortunately, it looks like there's no real way to simplify things down, except if we look, we have these zr theta terms. So we have a zr theta sine theta over r multiplied by cos theta, and then we will have a negative sine theta over r. One moment here. Actually, I'll leave that as is for now. Next, since this is already at half an hour, I'm going to skip to the end of having the d squared z by dy squared. The process is exactly the same. So we should get that that is going to be zrr sine squared theta plus zr theta cos theta sine theta over r plus zr cos squared theta over r minus z theta cos theta sine theta over r squared plus z sub theta theta cos squared theta over r squared plus zr theta sine theta cos theta over r minus z theta sine theta, or actually I just realized I can write this a little bit more efficiently, and minus z theta cos theta sine theta over r squared. Now, if we look at what happens when we add the two together, zxx plus zyy, if we go derivative by derivative, essentially. First of all, looking at our ZRRs, we'll have ZRR times cos squared theta from here, or rather I'll write it there. So we have the cos theta outside the brackets, plus sine squared theta from here. Then we have our ZR theta terms. We'll have minus 2 sine theta cos theta over r, which is coming from, where is it? Where are our ZR? Okay, yes. We have minus sine theta cos theta z theta r over r from that term there. And we have that. So we'll have minus 2 sine theta cos theta over r plus 2 sine theta cos theta over r. Sine theta cos theta over r. So the ZR theta terms are going to add up to 0. Then looking at our Z sub r's, we'll have Z sub r times sine squared theta over r plus cos squared theta over r. From there and there. Then looking at our Z sub theta thetas, you'll have sine squared theta over r squared plus cos squared theta over r squared. From that term there, we have negative sine theta over r times negative sine theta over r, giving us the sine squared theta over r squared. And we have z theta theta cos squared theta over r squared there. Then the last term that we need to look at is our z theta. That's going to be 2 sine theta cos theta over r minus 2 sine theta cos theta over r. From that term, oops, that should, my mistake, that should be r squareds on both. From that term in the z, the second derivative with respect to x, and from that, from the second derivative with respect, oops, is that the one? Yes, that's the one that I want. Those two, the second derivative with respect to y. So, that one was already accounted for as well. That's going to add up to 0 as well. So, from that and some application of the Pythagorean identity, we should end up getting that zxx plus zyy is going to equal z sub rr plus z sub r over r plus z sub theta theta over r squared. And if zxx plus zyy is equal to 0, then that means that since the two are equal to each other, that zrr plus zr over r plus z theta theta over r squared is equal to 0 as well.